Here in this video, we're going to continue to look at symmetry. This time we're going to look at how we can determine whether a graph is symmetric to the x-axis, y-axis, or origin algebraically. So here we have an equation, and we want to determine, is this equation going to be symmetric to the x-axis, y-axis, or the origin? And now instead of looking at the graph, we're going to do that algebraically. And if you recall, when we looked at something being symmetric to the x-axis, kind of graphically, we said what that means if we have our x and y axis and we look at the graph here, then that tells us if we have a point here where this is x, y, then down here we have the same point for the same value of x, but your y value is going to be negative. So in other words, positive y value gives you x, negative y value gives you the same x. So algebraically, we can check that by substituting a negative y in the place of y. So up here where we have y squared, we're going to make that a negative y. So we would end up with x minus, and notice I'm going to use parentheses, we're going to plug in the negative y. So the negative y is going in place of y, so that's negative y squared. Now, if we simplify this, negative y times negative y, if we square that, the negative becomes squared, so therefore that's going to be positive, but we still have the negative out front, so this would be x minus y squared equals 0. And if we compare this equation to the original equation, they're the same. And because they're the same, that tells us that this would be symmetric with the x-axis. Now, how can we look at the others? If we wanted to test the symmetry for the y-axis, well, recall, that means if we're symmetric to the y-axis, then I'll just simply look at a parabola again. And if we have a positive x, y, then what happens if we plug in a negative x? We still get out the same y value. So if we test this, then we can take and plug in place of your x, we're going to plug in a negative x. So now we're going to have negative x minus y squared equals 0. And if you notice, anytime I use substitution here, I'm going to put that term in parentheses so that negative x is going in for the x. So even though I don't really need the parentheses here, I just like to do that to remind us to be careful with your substitution. Well, of course, then this would simply be negative x minus y squared equals 0. And this does not look like the original equation. So therefore, it's not symmetric with the y-axis. And last, we want to look at, is this thing going to be symmetric with the origin? Well, if we recall testing symmetry with the origin, if we have the following graph, if your graph looks something like this, that basically says that if we have a point xy, then that means if you plug in a negative x, you're going to get out a negative y. So in this case, for the testing symmetry with the origin, we're going to do substitution for both. We're going to plug a negative x in for your x value, and then for the y, we're also going to plug in a negative y, and the negative x remains negative, and we have negative y squared. Once again, that becomes positive, but then we have the negative out front, so that's minus y squared equals 0. Now, if you notice, that does not equal the original, so therefore it is not symmetric with the origin. So this is the three tests that we can use for symmetry for the x-axis, the y-axis, and the origin. So for this one, it was symmetric with the x-axis. All right, here we have another example, and again, you may want to pause the video and see if you can work this out on your own. We want to find out, is this symmetric with the x-axis, the y-axis, or the origin? So if we want to test symmetry with the x-axis, Well, remember, for testing for the x-axis, we're going to plug in a negative y. So if I plug a negative in for your y, we get negative y equals x to the fourth minus x squared plus 3. And a negative y is simply just going to be negative y equals x to the fourth minus x squared plus 3. And this does not equal the original equation, so therefore it is not symmetric with the x-axis. And if we want to look at the y-axis, once again here we're going to plug a negative in for the x. So we get y equals negative x to the fourth minus, plug a negative x in for the x again, so it's negative x squared plus 3. And if we simplify this now, x to the fourth, or negative x to the fourth, so it's an even exponent, so a negative times a negative times a negative times a negative would be a positive x to the fourth minus a negative x squared, so once again that's going to go positive. And if we compare this to the original equation, they are the same. So therefore, it is symmetric with the y-axis. And if we want to test the origin, once again, that means we're going to plug a negative in for the y as well as for our x. And once again, once we simplify, we would have a negative y equals x to the fourth minus x squared plus 3. And that does not equal the original equation, so therefore it is not symmetric with the origin. All right, our next example, we have xy equals 4. So here we want to plug in, if we're testing symmetry for the x-axis, we're going to plug a negative y in for our y. So we would have x times negative y equals 4, which simply would be negative xy equals 4. If we multiply that, a positive and a negative is negative. That does not equal the original, so it's not symmetric with the x-axis. And we can probably see fairly quickly here the same thing's going to happen for the y-axis. We're going to plug a negative in for x, and we're still going to get a negative xy equals 4, so this is not going to be symmetric to the y-axis. And then if we test the origin, we're going to plug a negative in for the x and the y, and we'll notice that now when you multiply the two negatives together, you have a positive xy equals 4, and this does equal the original, so therefore it is symmetric with the origin. All right, I have another example here that we want to complete the following graph given that we have the indicated symmetry. So here we have a graph, we have part of the graph, and it says that it is symmetric to the x-axis. So how do we complete the rest of this graph? Well, if it has symmetry with the x-axis, then that means that if we have x, y, if that's a point on the graph, then that means that also the point x and the same negative y would be on the graph. So basically what that means is then our graph would continue down here like this. So that means we would have this point here, which would have the same x value but with the opposite y value. All right, one last example where we want to complete this graph given that it is symmetric to the origin. And again, maybe you want to pause the video and see if you can figure this out. If this is going to be symmetric to the origin, then that means that if we were to pick a point, remember, whatever this point is, and you could pick a point here and kind of make up some numbers if you're not sure how to complete this graph, but realize if this is xy, then that means the point negative x, negative y must also be on the graph. So if this point here would happen to be, let's say, over 2 and up 2, then that means that the point that goes negative 2 and down 2 would also have to be on the graph. And if this point here happens to be, say, over 1 and down a half, then that means you'd also have to have the point -1 and up a half. So your graph, if we complete this, is going to go up like this and down. And remember I said before that you can think of this kind of like a pinwheel. If you were to hold at the origin here and we were to rotate this graph around, then the black part of this graph would fall on top of the purple, and if you rotate the purple around kind of like a pinwheel, then the purple part of the graph would fall right on top of where the black part of the graph is located. And again, that's simply looking at positive x and y. So again, if you just were to make up a number and say, well, this point here is 2, 2, then that means that the corresponding point over here would have to be -2, -2. And if this point down here was 1, and let's just say -1/2, then that means that corresponding point up here would be at -1 and a +1/2. So you can kind of help make up some numbers there to determine how the rest of the graph will look. All right, so there are some more examples dealing with symmetry, and I do want to go back up here and point out one thing you may have noticed when we were testing symmetry algebraically. If you notice that if you are going to be symmetric with the x-axis, notice here what's happening with your y values. Your y values are raised to an even power. So that's kind of a quick check. If your exponent for your y variable is raised to an even power, then it's going to be most likely symmetric with the x-axis, as long as it's not being multiplied with some other variables possibly. And then if you notice here, we had symmetry with the y-axis. Notice here, all of your x variables are raised to an even power. If one of these exponents on the x was odd, then it would not be symmetric, because if you take the negative raised to an odd power, you're going to end up with a negative. So when we plug this negative in, we're raising this negative to an even power, and therefore it's not going to change the sign of the problem, so therefore you would end up with the exact same equation. So therefore it's symmetric with the y-axis. And then of course for the origin, you're looking at where if you plug in a negative for your x and y, that somehow they're going to cancel out. In this case, by multiplying the two negatives together, they become positive so that they equal the original equation.